Welcome to Math 31. This is a lesson on related rates. Related rates are really the big issue for this Unit 4 that we're looking at right now. And there's practically an infinite number of applications. So I'm just going to look at a few really common ones, and with maybe just a few sort of similar other ones like this is what you'll be tested on. So I won't expect you to be really good at applications you haven't seen before, although you will find that the methods are completely transferable. Related rates, like the name suggests, are really just comparing the rate of change of two or more variables. And important to note that this is with respect to time. That's what the rate would be. And up till now, we've really just dealt with rates of change where there's been one variable being analyzed with respect to another, and here we're going to have more. So if you were to consider a sphere, in this case a snowball that's melting over time, the formula for volume of a sphere is 4/3 pi r cubed. So if you wanted to calculate the volume at any specific for any specific radius, it wouldn't be a problem. But the volume would be changing with respect to time because it is melting. It would be decreasing. And if you were interested in specifically the rate of change that the volume was experiencing as time passed, we would write that as dV dt. So that's one rate, the change in volume with respect to time. And then the other one would be the radius changing with respect to time, because that is also going to be changing. It's getting smaller, so the radius is going to decrease as well. So that's dr dt. And we would call these related rates. Now, it means that we've got a more complex equation, and And there's a couple ways that we can tackle these problems. And once you get good at them, you find it fairly routine. But here's a simple illustration, same formula that we had before. So volume is equal to 4/3 pi r cubed. And we want to differentiate this with respect to time. So this really means that we're going to be using implicit differentiation, because we're taking the derivative with respect to a different variable. So with respect to time means that when we try to differentiate v, we can only express it as dv dt. I'm not going to use v prime like I had used for earlier implicit differentiation. Here it matters very much that we're indicating them with respect, that we're differentiating them with respect to time. So I'm not going to take any chances with this, no shortcuts. dv dt is equal to, now when we differentiate this, the only variable we have is r. So we do implicit differentiation, or the chain rule if you like. That 3 exponent gets multiplied by 4/3, giving us 4 pi r squared, and then dr dt. So this is the equation we would use that is relating the more dynamic system, the change in volume, with respect to time. And noticing that we have the variable r in it as well too. So instead of having two variables like we did originally, we've got dv dt, we've got r, and we've got dr dt. So it's 3 variables. So moving on, here's a question that's going to a fairly standard entry-level related rate problem. So air is being pumped into a spherical balloon, and its volume is increasing at this rate. So how fast is the radius of the balloon increasing when the diameter is 50 centimeters? There's our formula. Few things to be aware of. Diameter is 50 centimeters would mean that the radius is 25 centimeters. And that's what we're going to use. The big mistake is for people to plug in that r equal 25 right away. Reason it's a mistake is because that would be finding the volume. And we don't want the volume. We want to find out how fast is the radius increasing or changing. So note at the beginning what it is we're going after. We want dr dt. We want to find out the rate of change of the radius. So we then differentiate with respect to time. So this will look exactly like what we saw in the previous question. dv dt is equal to 4 pi r squared dr dt. And dr dt is the variable in question. That's what we want to find. Now the method I usually use is I differentiate it and then I take stock of what we have. If you look at the question, we're told that the volume is increasing at a rate of 100 cubic centimeters per second. We need to make sure our units are in order, centimeters, centimeters, and time units in this case would be seconds. But it means that dv dt is equal to 100. And the units would be centimeters per second. And this is occurring at r is equal to 25. And now we can substitute everything into the formula. Now I know you're thinking, manipulate first, right? And no, often I will. In this case, because it's simple, I'm not going to bother. I'll just put the values in. 100, I'm not going to put the units in. Just 100. I know the units are okay because we've got volume in cubic units, or dv dt, cubic units per second. And then 4 pi, and then r squared would be 25 squared dr dt. And then now if you divide it all out, because it's a, like a fairly routine one, we should be able to get a reasonable answer out of all this. So this is going to be 100 divided by 4 pi 25 squared equal to dr dt. And then do the simplification on it. Divide by 4, that'll give you 25. And then divide out a factor of 25 will give you 1. So we should end up for answer that 1 over 25 pi. Typically these ones will be in we'll have a pi in the answer, so we often will have exact values for them. Unless it states otherwise that you should round, assume that it's going to be an exact value. So we now can say that the radius is increasing at 1 over 25 pi centimeters per second. Now this is happening at exactly r is equal to 25. So be aware what this implies. It really is, like I said earlier, a dynamic system. We're finding how fast it's increasing at that time. We're not finding what the radius actually is. We know that it's 25. You're finding the rate that it's changing. So yeah, it takes a while to get comfortable with the differences. And some applications, of course, are easier to understand than others. Like motion ones make sense to everybody because we know velocity, we know acceleration. These ones, maybe not so much. So the next question is like this. Now, I think for this problem, it's not really a bad question. It's very similar. I'm not going to go through it unless there's a lot of interest in it. I'll give the answer, though. 5 over 64 pi centimeters per minute, I guess, in this case. So that's the answer, and because it's so similar to the previous one, I'm not going to worry about it. But try this one, and if you don't get that answer, please let me know, and I'll see what I can do about it. Next question. This is an interesting one. We're told that the rate of change of a triangle's base is 2 centimeters per second, and the rate of change of its height is 1 centimeter per second. And we want to get the rate the area is changing when the triangle's height is 10 centimeters and the base is 5 centimeters. There's an illustration of it, or it could be an illustration of it. Here's your height, and then there's your base. Now this is an innocent-looking question, but it really does involve something that will stretch us a little bit. Area is equal to 1/2 base times height. Now what's intriguing about this question is that there are 3 variables in the original. Now as we get deeper into this section, we will try to convert, say, base into height and height into base. It makes things a lot easier. For now, though, and for this question, we can't do that. So we're going to have to do a little bit more. The math is going to be a slight bit more complicated, but it should make sense. So before we launch into it, though, let's see what we're asked to find. So we're told the rate of change of its base. We're told the rate of change of its height. So this is a triangle that for some reason is changing shape. And we want to get the rate the area is changing. So find, or we want, dA dt. So the rate the area is changing at those specific values, H10, B5. Repeat, do not plug in that H10 and that B5 into the original question, because all you're going to get is the area at that particular moment, not the rate that it's changing. So you have to hold off. Don't plug in the 10 and the 5 until the time comes. And we do, as before, differentiate with respect to time. And when we do that, we're going to get a bit of a shock, because dA dt is equal to, now when we use this type of differentiation, we have to use product rule. So we take the derivative of 1/2 b. So that's 1/2. But then we have to note that it's dB dt. So we're using implicit differentiation multiplied by the height, because that's unchanged. And then the next one is going to be the 1/2 b stays as is, but we have to go dH dt. And now I'm going to take stock of what we have and what we want to find. dA dt, as I noted earlier, is the variable that we're trying to solve for. And then dB dt. Well, we have that. dB dt is the rate of change at the base. So we have that variable. The height. Well, we have the height. It's 10 centimeters, so we have that variable. The base, we also have. We know that that's 5. And dH dt, the rate of change, is 1. Now, because these values are positive, we know that they're increasing. So if they were negative, it would mean that, say, for example, dH dt would be decreasing. So they're positive, so they are increasing. So we're all set up. We simply plug everything in. So for this question, it's not going to involve any manipulation at all. It'll just be 1/2 times dB dt. So dB, the rate of change of the base, is 2. H is 10. So at H is equal to 10. I'll even write that down. At H equal 10, and B is equal to 5. And then plus 1/2 base is 5, and then dH dt, we have 1. So dA dt is equal to 10 plus, well, 5 over 2 is 2.5. So that's equal to 12.5. So we can say that the area is changing. You could say increasing if you wanted at 12.5 square centimeters per second. So I'm going to stop this introductory lesson right now, and then the next one is going to go through some more serious applications, volume questions, shadow questions, and ladder questions. So 3 very common applications. But this will get us going on them. So thank you for your time.